Hashtag Pluto, a distant and baffling planet. Pluto is a distant and baffling planet that was once considered a member of our nearby planetary family. Recent, ongoing announcements by renowned astrophysicists Neil deGrasse Tyson and Michio Kaku have brought Pluto back into the spotlight. They suggest that this cool world is on a potential collision course with Neptune. However, how could this work out, and what might be the consequences of such an enormous event? Are we seeing an intriguing cosmic characteristic, or is there something else to this impending disaster? Join us as we explore the possibilities of a Pluto-Neptune impact. Pluto, a former planet that was reclassified as a dwarf planet, remains a subject of interest and study in the cosmic community. This interest is evident in recent figures from leading analysts, indicating that Pluto's orbit is perilously close to Neptune's. Both Tyson and Kaku are raising alarms about a potentially risky collision between these two bodies, which could pose a significant danger to Earth. But how is such an event even possible? Pluto's journey around the Sun is unlike that of any other planet in our solar system. It takes a staggering 248 years to complete a single orbit, meaning that since its discovery in 1930, it hasn't even finished one full revolution. The intrigue doesn't stop there. Pluto's path is marked by its exceptionally elliptical shape, deviating significantly from the nearly round orbits of the major planets. What makes Pluto's orbit even more surprising is its inclination, determined to be 17 degrees to the ecliptic plane. This means the path Pluto follows is considerably steeper compared to other planets, adding layers of complexity to its orbital pattern. One of the most captivating aspects of Pluto's orbit is its intersection with Neptune's path. For around 20 years in each orbit, Pluto actually comes closer to the Sun than Neptune, going against what we might expect based on their positions in the solar system. This prompts the natural question: why hasn't Pluto collided with Neptune? The answer lies in the gravitational influences of other planets. The investigation of Pluto's orbit began shortly after its discovery. Initially, astronomers attempted to sort out its unconventional path. Unlike other planets, whose orbits lie relatively close to the ecliptic plane, Pluto's path stood out due to its steep inclination and elliptical shape. The mystery deepened with the realization that Pluto's orbit actually crosses Neptune's. The stability of Pluto's orbit amidst these complexities illustrates the intricacies of celestial mechanics. The three-body problem in space deals with determining how three objects, like Pluto, Neptune, and the Sun, move and influence each other with their gravity. It's like trying to predict where they will go based on their starting positions and how they pull on one another. In Pluto's case, this problem demonstrates how its orbit, Neptune's path, and the Sun's gravity all interact in a complex manner. The terms absolute libration and nodal libration, alongside zonal oscillation, are fundamental components of this puzzle. As indicated by astrophysicists, what's keeping all planets in their orbits is absolute libration. In the case of Pluto and Neptune, this term means that whenever Pluto crosses Neptune's orbit, it is situated no less than 90 degrees away from Neptune. This spatial separation is crucial in preventing their orbits from crossing. Nodal libration, on the other hand, refers to the vertical movement of a celestial body in its orbit. For Pluto, this means that when it comes closest to Neptune or any other giant planet, it is positioned well above their orbital plane, providing an extra layer of protection from potential impacts. Another key piece of this scenario is zonal oscillation, named after three scientists, Bond, Zipper, and F, who studied how objects move in space. It concerns how three celestial objects like Pluto, Neptune, and the Sun pull on each other with their gravity. This gravitational pull affects their movement. In Pluto's case, zonal oscillation helps us understand why its orbit around the Sun is so peculiar. Despite the apparent turbulence, this oscillation helps keep it moving smoothly over long periods of time. Zonal oscillation shows that even when things in space seem chaotic and irregular, certain patterns and rules maintain a semblance of order. All of these variables help keep Pluto's orbit stable, ensuring it doesn't crash into Neptune or wander off course. The three-body problem aids in understanding how these elements change based on the gravitational pull of celestial objects on one another. Studying this helps us learn more about Pluto, our solar system, and distant worlds and their stars. Numerical simulations in the late 1980s revealed that despite these stable properties, Pluto's orbit is indeed chaotic, with slight deviations in initial conditions leading to massive differences over millennia. However, these unique properties of Pluto's orbit have been found to maintain stability over extraordinarily long timescales. Monitoring this chaos, later programmatic insights have shown how the giant planets, like Neptune, Jupiter, and Saturn, influence Pluto's path around the Sun. Neptune has a special relationship with Pluto whereby, for every 2 orbits Pluto makes around the Sun, Neptune makes 3. This relationship helps keep Pluto's path stable. But Neptune isn't the only one helping. Jupiter's gravity also plays a significant role in shielding Pluto's orbit. In fact, Jupiter's gravity alone is strong enough to ensure that Pluto remains on a steady path for quite some time, even billions of years. It appears that Neptune, Jupiter, and Saturn are working together to ensure Pluto continues to move securely in space without running into trouble. These characteristics are significant in the broader context of the universe, maintaining the order and consistency of celestial bodies' movements. Without these stabilizing forces, our solar system would be a much more chaotic and unpredictable place. Bodies like Pluto could potentially collide with others or be ejected from their stable orbits, leading to impacts on other celestial bodies. For Pluto, discussions about a possible future crash with Neptune underscore the importance of understanding its orbit. This knowledge provides a clearer picture of the dynamic nature of the nearby planetary group. The case of Pluto illustrates how even the most seemingly unstable orbits can achieve a state of equilibrium through the complex interplay of gravitational forces and orbital mechanics. It also highlights the importance of continuous observation and investigation to better understand our position in the universe. Exploring the depths of space often leads us to confront the unpredictable nature of celestial bodies, and Pluto's orbit is a perfect representation of this volatility. The concept of orbital chaos, which refers to the delicate dependence of a celestial body's path on its initial conditions, is strikingly outlined in the case of Pluto. This means that even slight variations in the dwarf planet's position or speed can dramatically alter its long-term orbit. Using virtual simulations has been incredibly useful for researchers to figure out how Pluto moves in space. These simulations employ advanced mathematics to demonstrate how Pluto and other celestial objects like Neptune influence one another. By tweaking tiny details in the simulations, astronomers can see how even small changes can make a huge difference in where Pluto ends up. In the late 1980s, these simulations revealed something truly intriguing about Pluto's orbit. Despite having factors like absolute and nodal libration to keep it stable, its path can still be wild and erratic. If you start with just a tiny difference in where Pluto is or how fast it's moving, over many years its path can end up looking very different. Nonetheless, even with this chaos, Pluto's orbit remains stable for long periods, like billions of years. This suggests that Pluto's journey around the Sun has some kind of order, even if it appears chaotic at first. Predicting cosmic events, particularly those involving erratic orbits like Pluto's, presents significant challenges. The inherent unpredictability of these systems means that long-term predictions are often filled with uncertainties. While numerical simulations provide a robust means to understand and anticipate the future behavior of celestial bodies, they also highlight the limitations of our predictive capabilities. These models depend heavily on the accuracy of initial conditions and the complexity of the interactions they simulate. Any slight mistake or distortion can lead to vastly different outcomes, making precise predictions a daunting task. Moreover, the turbulent nature of celestial orbits like Pluto's serves as a reminder of the ever-evolving and dynamic nature of the universe. While we've made great strides in understanding space, the case of Pluto illustrates how our knowledge of the universe is still limited. Understanding the gravitational effects of the giant planets on Pluto's orbit provides valuable insights into the broader dynamics of the nearby planetary group. It shows how the presence and position of each planet can significantly affect the stability and trajectory of other bodies within the system. So why are prominent astrophysicists only now raising concerns about a possible collision between Pluto and Neptune, despite all these complex forces working to prevent such an event? Neil deGrasse Tyson, a notable astrophysicist and a key figure in popularizing cosmology, offers a unique perspective on the mysteries of our nearby planetary group, particularly the captivating case of Pluto. Tyson, known for his role in renaming Pluto from a planet to a dwarf planet, provides insightful commentary on the evolving nature of celestial mechanics and the public's interest in the obscure domains of space. His position on Pluto's renaming is grounded in the continually growing understanding of our solar system. He views the renaming not as a downgrade, but as a significant change in our evolving comprehension of the numerous bodies orbiting our Sun. His approach to celestial mechanics emphasizes ongoing learning and adaptation. He sees the complexities of orbits like Pluto's as an indication of how much more there is to discover in space. The interest in these questions, especially the potential interactions between Pluto and Neptune, highlights the dynamic and often peculiar nature of our solar system. Tyson's work emphasizes that the more we uncover about space, the more questions arise, pushing us to explore further and refine our understanding of the universe. Michio Kaku, another renowned physicist and futurist, offers an alternate yet complementary viewpoint on the mysteries of space, focusing on the often erratic forces that shape our universe. Kaku is known for his ability to connect complex scientific concepts with cutting-edge visions, making him a significant voice in discussions about celestial mechanics and the broader implications for humanity. Kaku's perspectives on Pluto and its orbit highlight the need for continuous observation and advanced modeling to predict and understand potential cosmic events. He sees the interactions between celestial bodies as a critical area of study, not only for academic interest but also for practical implications. The potential collision between Pluto and Neptune, for instance, isn't just a theoretical scenario but a reminder of the dynamic and often turbulent nature of space. Kaku's futurist perspective encourages us to consider the broader ramifications of such events, from their impact on our understanding of the solar system to the possible need for future space interventions. Both Tyson and Kaku converge on the idea that space is a realm of endless discovery, and that our current understanding, while vast, is still limited. Their emphasis on the need for continuous exploration and advanced modeling reflects the evolving nature of space science. They highlight the importance of understanding celestial mechanics as they currently are while also predicting how they may change in the future. The potential collision between Pluto and Neptune serves as a case study for the broader challenges and opportunities in space exploration. It underscores the need for rigorous scientific inquiry, cutting-edge technology, and a willingness to adapt our understanding as new information emerges. For Tyson and Kaku, the mysteries of space, exemplified by Pluto's orbit, are a call to action for the scientific community and humanity at large to keep pushing the boundaries of our knowledge. There is a general scientific consensus that for years to come, the orbits of Pluto and Neptune will remain stable due to their mean motion resonance and the various gravitational influences acting on them. Thus, a direct collision between Pluto and Neptune is extremely unlikely. However, the complexities and potential perturbations in orbital dynamics mean that astronomers must continue to monitor and study these celestial bodies to better understand their long-term behavior and any potential risks they could present. While the chance of a Pluto-Neptune collision remains largely hypothetical and is considered unlikely with our current understanding, it highlights the importance of ongoing investigation and observation in space science. Advances in technology, including more advanced telescopes and programmatic insights, will help astronomers refine their models and predictions, ensuring we remain abreast of the dynamic and ever-changing nature of our solar system. Tyson's perspective on Pluto's renaming and Kaku's emphasis on the erratic nature of celestial mechanics both underscore the need for constant examination and an adaptable understanding of our universe. The potential collision scenario, while representing the dynamic and complex interactions within our solar system, ultimately reminds us of the vast yet still unknown areas in our understanding of space. Through continuous research and observation, we strive to unravel these mysteries, ensuring that our knowledge keeps pace with the ever-evolving universe. The ongoing interest in Pluto and its potential interaction with Neptune invites further exploration of the broader implications of celestial mechanics. Understanding the gravitational dynamics at play can provide insight into the history of our solar system and the formation of planetary bodies. For instance, the unique characteristics of Pluto's orbit might hold clues about the early solar system's configuration and the processes that led to the current arrangement of planets. As astronomers continue to study these celestial dynamics, they utilize advanced technologies such as space telescopes and sophisticated computational models. These tools enable researchers to simulate various scenarios that could affect Pluto and its neighbors. For example, the role of other distant bodies in the Kuiper belt may also contribute to the gravitational ballet that shapes Pluto's orbit. Understanding these distant influences is crucial, as they may lead to changes in Pluto's trajectory over millennia. Additionally, Pluto's status as a dwarf planet raises questions about planetary classification and what criteria define a planet. This debate touches on the nature of scientific classification itself, which evolves as our knowledge expands. As more is learned about distant celestial bodies, the definitions we use may shift, leading to new insights about our solar system's complexity. Moreover, the potential for impacts between celestial bodies extends beyond Pluto and Neptune. The study of near-Earth objects, NEOs, has gained prominence in recent years, with scientists focusing on the tracking and characterization of asteroids and comets that could pose a threat to Earth. By understanding the mechanics that govern these bodies, astronomers can develop strategies to mitigate potential impacts. International collaborations are also becoming increasingly important in this field of study. By sharing data and resources, scientists from around the world can enhance their understanding of planetary dynamics. These collaborative efforts are crucial for addressing not only the risks associated with potential collisions, but also for fostering a greater appreciation of our universe. In summary, the exploration of Pluto and its interactions with other celestial bodies is a gateway to understanding fundamental aspects of astrophysics and planetary science. This knowledge not only enriches our comprehension of the solar system, but also emphasizes the interconnectedness of all celestial phenomena. Through continued research and observation, we can unlock new mysteries and refine our understanding of the cosmos.